All right. So let's just start by recapping what we talked about yesterday. So I'm just going to write this equation down once more because it's important. But I can generically... By the way, I've been told that I was not writing large enough yesterday, so I'm going to do my best to try to up that a little bit. That being said, if you're in the back of the room and can't read it, there are some seats up front, so like that might be another mitigating factor if it's not good enough. But I'll try my best. Okay, so just again, the various factors. This is to avoid double counting WIMP A and WIMP B annihilating with each other. This is the annihilation cross-section evaluated usually at very low velocities, although there are exceptions. This is the spectrum of annihilation products, in this case gamma rays per annihilation. This is just a geometrical factor, and then this is the number density of WIMPs squared, integrated over the line of sight and solid angle that you're observing. So this works for any number of targets. We did it with within the context of dwarf galaxies yesterday.
I'm sorry, what's the number density of WIMPs? I see mass and I see energy density.
Yeah, what's the ratio? The ratio is the number density, exactly. So we did a back of the envelope estimate for a dwarf like Draco. And we found for like 100 GeV WIMP with the thermal annihilation cross-section, you should expect just a few events appearing in the Fermi data set. Well, far too little to be detected. But you know, it goes like the 1 over the mass squared. So if you make the dark matter a little bit lighter and you stack a bunch of dwarfs, some of which are a little more promising than Draco, you can get some pretty interesting results. For the specific case of dark matter that's annihilating to bottom quarks, and you could have done many other things, but you get a constraint. Here's the thermal, 2 times 10 to the minus 26. Something like this, where the crossing point is right around 50 GeV. You might see I'm writing small already, but I've noticed. Okay, so what we've learned from that is if the WIMP's lighter than about 50 GeV or so, you tend to run into problems with gamma ray constraints under all of the various assumptions I've made. Some of these are, for example, we're annihilating to hadronic channels. If we were annihilating to leptons, it would be different. I'm also assuming that the dark matter has this canonical value for the cross-section, which need not be the case, but it's a good benchmark, and we're testing a meaningful fraction of all WIMP models when we do this sort of thing. So next, we turn our attention away from dwarf galaxies and towards the galactic center. So the galactic center is expected to be much brighter than any dwarf by factors of thousands, but the backgrounds are also much more complicated. We talked about the Nfw Halo Profile yesterday. I just want to remind you that the Nfw profile, which looks like this, where RS is a scale radius and R is the distance to the galactic center. This is something that comes out of numerical simulations of dark matter. More realistically, we don't expect most halos out there in the universe to be spherically symmetric like this. They tend to be oblate or prolate with axis ratios of maybe 2 to 1 in a lot of cases. But this is a pretty good description for the inner parts of halos, we think, most of the time. That being said, whereas this goes like 1 over R in the inner regions of halos, it's very possible that with the Milky Way, it's a little flatter or a little sharper, a little steeper. Don't take this as unquestionable truth. It's nothing like that. It's just a good benchmark estimate for what we think of the distribution of dark matter in halos. So Like I said, the problem with the galactic center, despite its brightness, is that there are considerable backgrounds to deal with. So I'm going to just make a list of the major backgrounds one has to deal with. The first is pion production. So here I have in mind a cosmic ray hitting some gas and producing, among other things, some neutral pions. Neutral pions decay 100% of the time to photon pairs. The distinction between gas and cosmic rays is just the gas is approximately at rest and the cosmic rays are highly relativistic. Or at least relativistic, I should say. The second is inverse Compton scattering, sometimes called IC or ICS. These are all common abbreviations. So the thing I have in mind here is I have a cosmic ray. It scatters off some radiation. Upscattering that radiation to gamma ray energies. It need not necessarily be gamma ray energies, but for the purposes of gamma ray backgrounds, that's what we're talking about. So when I say radiation here, I could mean a lot of different things. I could mean CMB photons. I could mean photons in the infrared background, or maybe UV emission from thermal objects or starlight. All of these things contribute. For the purposes of making backgrounds for an experiment like Fermi, a lot of it is scattering off starlight that's particularly important, but it's not the only thing that's important. The third is Bremstrolung. So here I just have in mind cosmic ray electrons scattering off of atoms to produce photons. And fourth, I'll just say gamma ray point sources. This could be a lot of different kinds of objects physically. They could be pulsars, they could be pulsar wind nebula, it could be supernova, supernova remnants, they could be blazars, any number of gamma ray emitting astrophysical objects. So we really have two ways to go about trying to separate these backgrounds from the signals we're interested in. One is just spectral information. So this is E squared times dE and dE as a function of energy. So generally speaking, the pion production contribution gives you a bump-like feature. That bump, exactly where that appears in E squared d and dE units depends on the spectrum of the cosmic rays you're dealing with. The harder that spectrum is, the more that bump shifts to the right. But that being said, this is usually at several hundred MeV to a GeV or so. That's the sort of range, we'll call this about a GeV or so, where the peak happens. So on the left, I'm going to write the spectral information. On the right, I'm going to comment on the GeV. On the right, I'm going to comment on some of the angular or morphological information that you can use to separate. So this pion signal should be proportional to the number density of cosmic rays present and the number density of gas. We have ways of estimating how the gas is distributed in, say, the Milky Way. One thing you can do is look at how much starlight is being absorbed by dust along a line of sight And usually one assumes that the gas and dust densities trace each other to a high degree of approximation, and you can generate at least 2D gas maps that way. That's one way you can go about this. You can also do things like noticing where all the cosmic ray sources are and how they're distributed, and as a result of that, make estimates about where these cosmic ray densities are likely to be high and low. So you get some, although some imperfect information about where the pion production should be taking place. All right, so the second background on this list is the ICS component, the inverse Compton. Again, the spectrum depends a lot on the spectrum of cosmic rays that are present, and to a lesser extent, the spectrum of radiation. But there's not a distinctive bump feature here. It's a little bit smoother compared to the pions. And here we're, of course, proportional to the densities of cosmic ray electrons and the inner density of radiation. So one important morphological distinction here is that the gas could be clumpy. There could be small scale power in the gas distribution, but there really can't be in radiation. There's no physical mechanism to pull radiation together, so we expect the radiation density to be pretty smooth. I mean, the CMB is awfully smooth, starlight is pretty smooth, et cetera. And then there's a component from Bremstrolung as well, and it's usually a little bit softer, dominates at low energies typically. And in this case, I won't write it down, but the Bremstrolung component goes, again, like the amount of gas and cosmic ray electron abundance.
I'm sorry, for some reason I was not listening. So you have NCR, comma, something for
Proton, that's yeah.
And electron for the next one?
That's right.
Okay.
Because it's protons that scatter with gas to give you the pions, and ICS comes from cosmic ray electrons. And they need not trace each other in a perfect way. So, what you usually do, and there are variations of this, different groups approach this sort of problem in different ways, but typically what you do with like a Fermi data analysis looking for dark matter signatures in the galactic center is you create a series of morphological templates and then add them together in each energy band independently to generate a spectrum for each template. So for example, I might have a pion, ICS, Brem, known point source catalog, Nfw squared, isotropic templates, like that would be a common combination you could do. So you have some map which tells you where you think the gas and the cosmic rays are. You have some other map which tells you where you think the cosmic rays and radiation are. Some other map that tells you this, a known point source catalog. Nfw squared. Squared, I'm really talking about here just calculating what the morphological part of this equation says. So that's the dark matter template. And then there's, of course, an isotropic background from everything going on in the universe. So in one energy bin, okay, maybe say 1 to 2 GeV, you take all the photons, you sum these maps together with arbitrary coefficients, and you constrain the coefficient of each template. And then you repeat that in each bin. And when you do that, you find a feature that looks like this, peaking just above a couple of GeV, or a GeV or so. Associated, I should say, with that template. It's now the case that, I don't know, 6 or 10 or something different groups have done this, and a consensus is formed about the broad features of this excess. Everybody agrees this excess is there, and we all agree about its broad characteristics. Depending on exactly how you do this sort of analysis, you do get slightly different answers. For example, some groups find there's more power up here than others, and depending on how you model the point sources, you can get different answers down here as well. But the fact that there's an excess that's bright, that peaks at a couple of GeV, is agreed upon by all analysts of the data at this point. This is a picture of the spectrum picked up by the Nfw squared template. So I want to be careful to say that so in a sense it is what you're saying, but it is not a subtraction of background. It is a fit of the signal component to the global template analysis.
So what you're actually seeing from the sky is some sort of a steeply falling curve, which is all the things that are on the blackboard, which is hidden there, and then maybe something smooth sitting on top of it. Is that how?
So let me draw a cartoon, okay? All right. Let's say I have one angular dimension, and I have some flux, all right? So instead of it being a two-dimensional sky, now it's a one-dimensional sky. And instead of having 1, 2, 3, 4, 5, 6 templates, we're going to have 2. I'm going to have a template that looks like this, okay? And I'm free to move it up and down. And I have a template that looks like this, and I'm free to move it up and down, okay? Now, this is just a copy of it, but now I'm going to put some data on here. Let's say you were to measure that. Well, this template is too steep, and this one's too flat. So what you're going to find is that your best fit is going to be something like this with some error bars around it, plus something like this with some error bars around it. And now I have coefficients for those two templates. If I'm saying this is the thing I'm calling signal and this thing is the thing I'm calling background, then I calculate in each energy bin the coefficient associated with this template, and that's, say, this, and I do it each time to construct the spectrum.
So how big is the contribution from the other ones?
Well, so there are some clear ways that allow you to tell that this is not primarily coming from the pion production. For one thing, the Nfw morphology looks nothing like the pion morphology. The pions follow the gas, which is a distribution along the plane. The Nfw squared is approximately spherical, extending well north and south of the plane. That is the key morphological distinction that allows you to do this. It's also the case that the pions do peak at lower energies than this. So there's some spectral information that allows you to discriminate this as well.
Do they actually peak a little bit below GeV, like right on resonance?
Well, so if I produce a pion, and in the rest frame of that pion, I always produce 2 impion over 2 photons. And then when I boost that pion, one of the photons is above impion over 2, and one's below it. So in dN, dE units, it's always flat, no matter what the spectrum of cosmic rays is. But then when you multiply it by E squared, the peak moves depending on the spectrum of those cosmic rays. But for a typical cosmic ray spectrum, like we model and observe in the galaxy, these things tend to peak at 700, 800 MeV, something like that.
So if I'm going to understand this correctly, the 1 degree freedom you've got is you can just move the signal as it were up and down. You can make it more or less of it. You can't move it side to side or like change the slope of a line that you would have or anything like that. So then is that, and then
So different groups do different things. So the answer to your question depends a little bit on which group you're quoting. So in my most recent template analysis, what we had is we in fact had one combined template, which we called this, okay, which we derived from a Galprop-like model, or we could just take the one the Fermi collaboration provides, things like this. They don't vary that much. We had a second set of templates, which was set to the known point source catalog and give you a different morphology. And we didn't mess with the morphology. We just took it as face value. Isotropic is straightforward enough. And then we took this template and we considered departures from NFW. We had degrees of freedom in that. And then we did it truly independently in each energy. One thing you might worry about is if this didn't give you a smooth line, or if any of these templates had non-smooth spectra, that would tell you there's probably something buggy about what you're assuming about your templates. So there are lots of different ways one can do this. Some people do global fits, where they assume not only things about morphological templates, but things about the spectral nature of the templates. But the point, I guess, I'm trying to make is these groups have done these things with a variety of different techniques, and they all reach the same conclusion, making me not very worried about the large-scale features of the excess.
So when you say template, what exactly is that? Like some function over the sky?
Yes, exactly. It is a spatial template.
So when you boxed those and said you came up with some template that combined all those and like fixed the ratios of the coefficients of those?
That's right. And yes, effectively yes. So I have some map. So I pixelize that map, and I know the constant proportionality of the gamma ray flux in each map for each template.
So then when you say you get this excess by looking at the NFW squared template, does that mean you're only looking at the excess over what that particular function would? You're not including like high zero contributions or anything else?
No, you're including that. So the thing I'm calling the excess, and this goes back to Tom's question, the thing I'm calling the excess are the coefficients to this particular template. Now I could plot something analogous to this to each template in my fit. Okay? And it would tell you what the spectrum from that physical set of processes is. So the fit determines all of those coefficients. But usually we just plot the excess one because that's the one people are trying to extract. The others are not nearly as interesting, of course.
So your set of coefficients is one for each energy band and one for each pixel, is that?
No, it's for one for each template and energy band. Hold on a second. Because by starting with the spatial template, you know what the ratio of, for example, pions in that bin and that bin are. So you don't need to do them independently. If you did that, you would never be able to make progress. There would be too many degrees of freedom. You would never be able to solve the problem. Yes?
Yeah, so well, I have a question, but
Yeah.
also I guess one way to rephrase that is that there are photons in the data that are better captured by the NFW squared template than the other templates, the background templates, and they're not getting absorbed into the other templates. My question was, so did you mean that in your analysis at each energy bin you also like the gamma flow of the NF?
Oh, you mean the slope of the, yeah, that's one, well, not at, okay.
Or you let the profile.
You would repeat the exercise many times for different values of that slope, and you'd compare the quality of the fit in each case.
So you find like the best fits.
That's the sort of thing, and ideally you put error bars on that on each free parameter. Yeah.
All of these components, all the known API is the shape, and the only way of fixing the coefficients is by the display. Or at least for some of these components, do we know the expected flux?
We know things about the expected flux, right? I mean, we don't know it to two significant figures, okay? But I would say we know the first significant figure pretty well, okay? Yeah, I mean, we have some range that we would consider reasonable. If there were 100 times more inverse Compton scattering being picked up in our template analysis than our models had predicted, we would assume something's broken. Or that for some reason, something was dumping a bunch of cosmic ray electrons in the galactic center that we didn't understand. We'd have to consider things like that. So we do have some information to work on there. As it turns out, the best fit coefficients for all these match pretty well with the cosmic ray models that were written down prior to Fermi. So there were no big surprises in terms of cosmic ray physics revealed by Fermi. Okay, so I'm just going to write down the basic set of characteristics of the excess, and I'm where different groups disagree, I will try to make that clear. So first of all, it's bright and statistically significant. Now, how statistically significant depends on exactly which techniques you use and how you quantify this. But no one thinks that this is a statistical fluctuation. It just simply is not. I think the right answer is somewhere between 10 and 30 sigma. Okay, it is not a subtle effect. It extends radially outward from the galactic center to at least, I think 10 is super conservative. I would say 20 degrees clearly. Some papers see it out to 30. But the significance falls off as you go farther away. But it is not anything like a point source. It is extremely extended, multi-kiloparsecs in spatial extent. Yes?
If the NFW template was functionally in the wrong shape, like if there was like a different thing, what would that do to this? So look at this excess.
Yeah.
What if you had an excess that didn't map to any of the templates, that was just a weird shape that didn't agree with anything?
So here's what you would do to explore that possibility. You would put in a different set of templates and see how, you would take out the NFW and put in something that was different. And experiment with that in a bunch of ways and see if the fit improves in any measurable way as you do that, or if it gets worse. For example, to extents. Okay. To test this, we took an NFW template that was truncated at a given radius. And we saw, does the fit get worse or better? And if you truncate it at 30 degrees, nothing changes. You can't see anything out there. But if you truncate it at 10 degrees, the fit gets a lot worse. Okay? Similarly, we're not strictly using NFW. We start with something like NFW. Do I still have it here? Yep. But where there's a 1 over R, we put in an arbitrary power. We call it alpha, so it's 1 over R to the alpha in the small r limit. We vary alpha, and we see, does the fit get better or worse? And in fact, we find that the best fits in terms of a dark matter interpretation is you want a dark matter density profile that goes a little bit steeper than NFW, 1.1 or 1.2, maybe 1.3, something in that range. I'll say 3. I don't think anybody is arguing for a number outside of that range right now. So it's just slightly steeper than NFW. And a lot of other templates have been considered. We've used templates that are either elongated along the plane or elongated perpendicular to the plane, various things like this. Sorry, say again? That's correct. This is, we have no priors on this from the n-body. The fact that it's similar to NFW is intriguing, but we did not assume it was NFW or anything like this. Although the first time I fit to the data, I put NFW in, saw that it worked pretty well, and then I started to tweak it from there. Yeah? Good. So in the inner 1 degree, about 1/3 of the photons are attributed to the excess.
What's the number of excess events in that 1 degree?
It's an order 1,000, something like that. Okay. To normalize the overall signal, this requires an annihilation cross-section. Again, if you interpret this as dark matter, which is not the only interpretation. But if you treat it as a signal of annihilating dark matter, it turns out that the normalization requires a cross-section of around 10 to the minus 26 cubic centimeters per second. Depending on exactly what you assume about, say, the dark matter density and the scale radius and other sorts of things like this, you can move this up or down by a factor of a few. But this is about the right answer. Take the twiddle seriously. It could be, if you rule out exactly that number, that's not necessarily problematic. It could be 6 times 10 to the minus 27. It could be 3 times 10 to the 26, anything like this.
Should that be centimeters
cubed. This is the sigma v, right?
Yeah, okay. I got the secret in my notes.
I may have been writing it wrong at some point too. And then lastly, like the spectral shape that I wrote up there, for the case of annihilations of BB bar, and again, this is not the only option, you want a mass between roughly 35 and 70 GeV. So this is a range that this is pretty big, and the main reason it's so big is the details of the spectrum on either the very high or very low end does depend on exactly how you treat your templates. These features called the Fermi bubbles really strongly affect exactly the spectrum you get above about 10 GeV, and that impacts your fit. How you treat faint and difficult to resolve point sources can really strongly affect your spectrum below half a GeV. So exactly how you treat this can shift your mass up or down by a non-negligible amount. If I assumed other sorts of annihilation channels, I get different numbers. If I go to taus, for example, which is another common benchmark, I want a mass that's closer to 10 or so GeV. If I go to lighter types of quarks, I want a mass that's a little bit lower than the range shown here, maybe 20 to 50 GeV or something like this. So you can play around with different models.
Are there any analyses that let the branching ratios?
Sure, yeah, there are.
Do they find a consistent mass region?
Yes, but it's basically an interpolation between the various models. So yeah, there are lots of papers that try to do this in various model contexts. Yes. But roughly speaking, for hadronic channels, something between 20 and 70 GeV can generally do the job for this cross section and this profile. So this is attractive for a lot of reasons. I've certainly gotten pretty excited over it in the last, I guess it's been almost 10 years since we discovered this signal. But a lot of interest has recently been directed towards another possible interpretation, namely that these gamma rays are not coming from annihilating dark matter, but they're coming from a large number of unresolved pulsars. So I'm going to go down a little road of astrophysics here, assuming that not many of you have experience with things like pulsars, just to give you a basic picture of what we're talking about here. Yeah?
Based on the parameters about assuming dark matter in the galactic center, and doing similar template analysis, how long before we can see something like this coming from Drake or other
Yeah, so if I go to this plot, you see where the limit is. Those sorts of parameters I'm talking about are right around here, okay? So in other words, we're right in the boundary of that. If I take the top level cross sections that fit the galactic center, that's probably already ruled out by dwarfs. If I take the minimum one, it's not clear that Fermi will ever see it in the dwarfs. If I take the middle value, you should already see some excesses in the dwarfs, and they should get bigger as time goes on. So it's in a very interesting regime for dwarfs. I'll just mention the thing that's exciting about dwarfs going forward is the LSST program is going to likely discover 100 or 200 new dwarf galaxies in the Milky Way. And you can take the already existing Fermi data and see if there's excesses from those directions too. So you expect this limit to get stronger by a factor of a few just because of the new discoveries of dwarfs. And there could be, non-negligible excesses contained in that if the dark matter interpretation of the excess is real. I'm not sure I remember it right, but I think 2022 is the first light. Does anyone actually know? Don't quote me on that, but that's what my... Sorry?
I think it launches around 2020, so that sounds,
Oh, it's a ground-based, sorry.
but they start.
Okay, first slide in 2020. Okay. All right. So not very long. Thank you. Okay, so pulsars. So the reason why pulsars are such often talked about background for a dark matter search is that they do have very similar spectral shapes to a 30 or 40 GeV WEMP going to BB bar. They're not identical, but they're close enough that it's very plausible that if there were a lot of pulsars, they would generate a signal that spectrally would look a lot like what we're seeing in the galactic center. So what a pulsar physically is a rapidly spinning neutron star. So a supernova occurs, leaving a neutron star behind. A star like the sun rotates on its axis once a month. When you collapse it to the size of a neutron star, it spins up by conservation of angular momentum to a period that is, multiple times a second, typically. Okay.
This is fairly unbelievable. How do we know how fast a star is rotating? How exactly are we observing?
I don't know, maybe sunspots or something? I'm actually not sure. But do the sunspots actually rotate with the bulk motion of the star? There you go. Okay, sunspots will do the trick. I'm sure there are other ways too, but that was.
That doesn't work for neutron stars.
Well, no, but okay, it's very easy to tell how fast a neutron star is rotating, because once it collapses, it's rotating, multiple times a second, or maybe one time a second, or something like this, and it has a very, very strong magnetic field for the same reason. So you have something with a kind of normal star's magnetic field, and you collapse it, and conservation of magnetic flux means suddenly there's a 10 to the 12 Gauss field on its surface. And under those conditions, they start to accelerate beams of particles, radio emission and such, along an axis. So now we have a rotation axis and a beam axis, which means that every time you rotate this thing, the beam sweeps out like a lighthouse in different directions. And to an observer, say here, once per rotation, the beam hits you. This is why they're called pulsars. So it's very easy, if you're looking at a pulsar with a beam pointed in your direction, to measure its rate of rotation. So as the pulsar persists and rotates, that kinetic energy in the rotation gradually gets transformed into radiation of various kinds. That's the power source of the pulsar. A lot of this power is in radio, a lot of it's in gamma rays, and perhaps in other wave bands as well, but mostly it's radio and gamma rays. I'm just going to simply define the gamma ray flux from a pulsar as this efficiency factor, eta gamma, times the rate of change of the kinetic energy, rotational kinetic energy. So this is just a definition of what I'm calling the efficiency. But then I can write this like the following, where P is the period, P dot is the time derivative of the period, and I is the moment of inertia of the neutron star. The thing that pulsar experts generally think is the leading effect causing this slowdown is something called magnetic dipole breaking. So if you just take a magnetic dipole and spin it, it will slow down in a calculable way. It's kind of an idealization. It's something like a spherical cow, but it's probably about right. And that gives you a rate of change of the period that I'm not going to derive, but I'm just going to quote it for you. This is 10 to the 8.5 Gauss. And that's the period in milliseconds. These are kind of benchmark numbers for a millisecond pulsar, and I'll talk about the distinction between young pulsars and millisecond pulsars in a second.
I'm sorry, what's the exponent on that? You've got B over 10 to the something.
That's B over 10 to the 8.5 Gauss, quantity squared. You'll notice P dot is unitless. It's a inverse time times time, so it's exactly what you would expect. And now I can write this, and I'm going to use the astronomer's units of 10 to the 34 ergs per second, scaled to the efficiency, the magnetic field, period, come back to that in a second, but first I want to draw an important diagram. A ton of information about pulsars can be understood by looking at at pulsar populations in the period and time derivative period plane. We have milliseconds down here and seconds up here. And there are lots of orders of magnitude here, but I'm not going to draw them. Well, I guess I can. This is 10 to the minus 10, and that's about 10 to the minus 20. If you want a real version of this, just Google pulsar PP dot diagram, and you'll find a lot of them, but I'm going to kind of give you a cartoon of it. So you wind up with a population called young pulsars that roughly populate this sort of area. Oh yeah. These are lines of constant magnetic field. And if a pulsar starts here, it essentially evolves along those lines. So, as it slows down, its magnetic field shouldn't change, at least not very quickly. So it basically evolves in that way. The characteristic time or lifetime follow lines like this. That's kiloyear, megayear, and gigayear. So basically, we think young pulsars are formed around here, and after 1 million years or so, they've generally evolved to there, at which point they are much less bright than they started.
But they always stay in that same little area of young pulsars?
Well, always is a tricky word, but they do for while they're young pulsars, so they evolve like this. But eventually they become pretty faint, and you stop noticing them. They stop doing much of anything. And now this is where millisecond pulsars come in. These millisecond pulsars are former young pulsars that after they spun down and became faint and quiet, either had or acquired a new companion star. And through interactions with that companion star, they acquire some of that angular momentum, and they get spun up to a higher frequency again, a much higher one. In fact, they find themselves living in this area. So it turns out that these pulsars are much, much longer lived. They have typically gigayear times lifetimes, in contrast to kiloyear or megayear for young pulsars. And they have much lower magnetic fields, in the ballpark of 10 to the 8 or maybe 10 to the 9 in the most extreme cases. So wildly lower magnetic fields. But if you consider the fact that their periods are much higher, or much faster, lower periods, faster rotation, and lower magnetic fields, it turns out that these things roughly cancel in a way that means they have about the same overall energy budget. And their measured efficiencies, the gamma rays, are not all that different. So it turns out that a typical millisecond pulsar produces a gamma ray emission in the ballpark of 10 to the 33 or 34 ergs per second, which is a lot of energy. So when people talk about the galactic center excess in pulsars, they're usually talking about millisecond pulsars. Can anyone tell me why they would be more attractive than the young pulsar interpretation? Can anyone speculate? Yeah.
Just as you'd see young pulsars twinkling on a time scale you detect, whereas millisecond pulsars.
Okay, good. So with a radio telescope, it might be easier to detect the pulsations from a slower spinning pulsar. That's true. That's not the main reason why they're considering this, but that is a reasonable point.
So based on my understanding of your diagram, the young pulsars are brighter overall, so like you could actually see them. The millisecond pulsars happen after they're closer to the end of their life, after they're dimmer, and so it would be a lot harder to see the star itself. You just see that pulse.
So here are the two scalings that determine their power. So it goes like b squared over period to the fourth. And it turns out that if you compare these, the difference in the magnetic field approximately cancels with the difference in the period, leading to about the same twiddle, about the same total power. So one is not brighter than the other.
I don't mean the pulses, I mean the star itself.
What do you mean by the star itself?
So like you see an increase when it hits the pulse, but when that axis is not facing you, it's still a luminous body.
I mean, not in a way that we can never measure, right? I mean, these are neutron stars. Neutron stars are to first order invisible. Yeah, yeah.
So I maybe misremembering something, but I think I remember that in the galactic nucleus is mostly older stars, and that's why you favor older pulsars that have then gotten longer, gotten faster spinning rates through acquiring it rather than being newly born pulsars.
So that's very close to what I have in mind. Let me put it in my own words. So you're right. The galactic center is mostly full of old stars for evolutionary reasons. But more generally speaking, we have a pretty good idea what the star formation rate in the galactic center is. And that should tell you how many young pulsars should be there right now. Because they evolve so quickly, you only care what the star formation rate was like in the last mega year or something, right? And that's a measurable quantity, okay? And you can calculate how many young pulsars there should be, and it's not anywhere close to the right number, okay? There just aren't enough there. With millisecond pulsars, we don't know how many should be there, okay? We've never detected a millisecond pulsar anywhere near the galactic center, but we're not sure exactly that if there were millisecond pulsars there, we'd be able to see them very easily either. So it's possible there are lots of them there. To explain the galactic center excess, you'd need in the ballpark of 10 to the 4 active gamma ray millisecond pulsars. And there I'm not counting the ones that are not beamed towards us. So 10 to the 4 with beams in our direction, maybe several 10 to the 4 total ones. My view is that it's a little difficult to explain this in terms of millisecond pulsars. If you take the luminosity function of the millisecond pulsars we observe, either in globular clusters or in the plane of the Milky Way, and you postulate that the luminosity function will be the same in the galactic center, a reasonable guess, you should expect that Fermi should have already detected several, if not several tens of these millisecond pulsars. And there really are very few candidate point sources that could be millisecond pulsars in the Fermi catalog. There are a couple that maybe could be. But there's definitely some tension there. I'm not going to call it anything more than tension, but there is some tension there. And secondly, millisecond pulsars are generally traced by populations of things called low mass X-ray binaries. You can think of these as the thing that's about to become a millisecond pulsar, like the precursor to a millisecond pulsar. And we have really good X-ray searches for LMXBs in the galactic center, and we don't see nearly enough of them to lead us to expect there to be a large millisecond pulsar population. So these things together make you think that maybe there are not enough pulsars there to explain it, but I think it is definitely the leading astrophysical interpretation for a good reason, and I'm certainly not prepared to say that millisecond pulsars are ruled out as an explanation.
So part of the argument for that is that the morphology of the concepts in the galactic center look like they're coming from some unresolved point sources.
Good, that's what I'm going to talk about next.
Right. So I was going to say, what are some other compelling
Point sources?
Yeah.
Yeah, there aren't any. Yeah, I mean the only gamma ray point sources that are known, or only class of gamma ray point sources as a spectrum that's anything like this at all, are pulsars. Yeah, and that's why we're talking about them. So what she was just alluding to is an interesting line of analysis of Fermi data that suggests, I think it's too far to say that it suggests a pulsar interpretation, but it suggests a point source interpretation of the Fermi excess. So what they did, and this is Lee Slatcher, our own Tracy Slatcher, Lee Lisanti, Way, I think that's all the authors. What? And Ben Safdie. Did I not say that? Yeah, Ben Safdie. They did a kind of template fit. think I have this here, which is similar to this sort of template fit, but in addition to these templates, you include another set of templates that are non-Poissonian in nature. What I mean by that is when I write down, for example, my isotropic template, it says this pixel has a mean expectation of having 5 photons in it. And then when I calculate the likelihood function of a given model, I write a Poissonian distribution around 5, and I weight the likelihood by departures from that median expectation. A non-Poissonian template might say, well, the average is 5, but there can be really big tails in all directions. It might be that you get 1 out of 10 of these things has 50 photons and the rest have 0. Okay, like that's a non-Poissonian template, and it's what you'd get if there's small-scale power, such as point sources in your data set. And this sort of analysis does find considerable evidence for small-scale power. There are different ways to interpret this. One is that the excess is coming primarily or entirely from an unresolved point source population. Another interpretation is that you are not including the right amounts of small-scale power in your various background templates. And I think it's an open question at this point. I'm not going to get into the various details of this argument. But I will entirely agree that this provides support for a point source interpretation. But at the same time, I think there are lots of arguments to bear. And what I'm really excited by is that in the next several years, we should expect that if there are all these millisecond pulsars in the galactic center, the radio survey should become sensitive enough to start detecting lots of them. If they don't find them, or they don't find them in large numbers, I think that would give considerable support to a dark matter interpretation. Similarly, in a similar time scale, LSST plus Fermi and other telescopes will be more sensitive to dark matter and dwarfs. And like I said, this is at a level of sensitivity where you could hope or even expect to test the dark matter interpretation of the galactic center excess with these other systems, in which pulsars should be entirely irrelevant. All right, so at this point, I'm planning to transition to cosmic ray searches, but before I do, are there any, yes? So when you add all of these degrees of freedom having to do with the non-Poissonian distributions in this analysis, it means you have, just to make it computationally tractable, you have to lose some degrees of freedom somewhere else. And what they do is they don't use much of the spectral information. They basically have one big energy bin. So the spectral information gets lost at the expense of the fine structure spatial information. Okay, any questions before we transition to cosmic ray searches? Okay. So this whole time we've been talking about gamma rays, a theme has been coming up over and over again, which basically comes down to, if you want to tell your signal from your background, you need to parse this with a combination of spatial information and spectral information, right? Those are the two handles you have to try to tell what photons might be statistically likely to be coming from dark matter, and what other photons more statistically likely to be coming from some diffuse background or point source or something. Cosmic rays have it a lot harder. Okay, so if you inject a cosmic ray somewhere out in the halo, either a background one or a signal one in terms of dark matter annihilation, it doesn't travel in a straight line to us. It moves in a complicated random walk, diffusing through the network of tangled magnetic fields that fill the Milky Way. So when they reach us, they're approximately isotropic. Any departures from isotropic are not really useful. So you don't have any angular or spatial information to work with at all. In the case of cosmic ray electrons or positrons, you furthermore lose a lot of your energy information, your spectral information, because as these particles diffuse and travel through the Milky Way, they lose energy steadily through a combination of processes we'll talk about. So this is a much harder game. There is, however, one big advantage of cosmic ray searches for dark matter. Can anyone guess or know what that is?
A lot fewer things just spit out antimatter.
That's right. So whereas gamma rays are their own antiparticle and therefore astrophysical processes make lots of them, astrophysical processes make relatively little antimatter. Okay. So we think we can calculate in a lot of cases how much antimatter should be made in these processes, and you can look for excesses over those expectations as indications of dark matter annihilation products. Because in the vast majority of dark matter models you'd write down, the annihilations make equal quantities of matter and antimatter, which is much higher than astrophysical processes that we normally think about. Okay. So I'm going to start by writing down a version of the cosmic ray transport equation. Okay, so this is the partial time derivative of the differential number density of cosmic rays with energy as a function of the energy, location, and time. And this first term I'm writing down describes the diffusion of those particles. And then another term I'm going to write down here describes the convection of those particles. And I'll in words tell you what I mean by those things in a second. And then I have a term which describes the energy losses of the particles. And lastly, I have what I just call the source term, which describes how the particles, where and how and with what spectrum the particles are injected into the Milky Way. This isn't the most complete version of this equation. Sometimes people include terms associated with processes like convection, secondary reacceleration, spallation and decay and things like this. But this is, for our purposes, I think, detailed enough.
Energy is a function of energy in x.
Where do you see that?
Third term.
This is the rate of change of energy as a function of energy in x, the location. So a particle loses energy at this rate if it has that energy at that location. Sorry?
What was that Q again? What is it?
Q is the source term. This is when, where, and with what spectrum particles of a given species are being injected into the diffusion zone, which is that of the Milky Way.
Can you repeat what the second and third terms were? I had the first
Good. Tell you what, let me just go through all the terms again because I bet people are confused about a lot of them. This is the time derivative of the cosmic ray spectrum, so how it evolves. By the cosmic ray spectrum, I mean the number per energy of a given cosmic ray particle at a location, energy, and time. This term describes diffusion. You can think of diffusion just as a random walk process. It doesn't have any spatial preference. You just walk in some random direction and take a new step in a new random direction, etc. This quantity d of E and x is just a diffusion coefficient. It's just a parameterization of the effects of diffusion. This term describes convection. Convection, unlike diffusion, is directional. There's a preference for cosmic rays to move in one direction relative to another. Within the context of these sorts of problems, you usually talk about convection as being the sort of thing that drives particles away from the disk of the Milky Way. Okay, so maybe they get injected somewhere near in the plane from a supernova remnant or something, and then they random walk, but they random walk with some preference away from the plane, escaping the diffusion zone. This term describes any energy loss processes that might be involved. And all that physics is included in this term. dE, dt describes whatever processes are causing these particles to lose energy. For protons and antiprotons, this term can safely be neglected. They don't lose energy in any reasonable time scale. They just travel without interacting. Electrons and positrons are another story. Through a combination of inverse Compton scattering and synchrotron, they lose energy pretty quickly, especially for higher energy particles. And then lastly is the source term. This describes the distribution, spatial distribution and spectrum and time profile at which cosmic rays are injected. If I'm talking about the source term from dark matter annihilations, this will look like Nfw squared, for example, and with the spectrum given by dark matter annihilation products. If I'm talking about the background cosmic rays, this term might describe where all the supernova remnants are and when they exploded and what they injected into their environments. It could also include things like secondary cosmic rays. What I mean by that is, imagine a proton's flying through the interstellar medium. It hits something, and a positron comes out. Okay, that positron was injected into the ISM at that point, so you could include secondary production in the source term as well.
So when you do a random walk, then you use things change directions instead of bouncing off other stuff.
So the random walk is dictated by magnetic fields.
Oh, right.
Okay, so that doesn't change anything about the particles except the direction they're moving in.
Those of us who are more familiar with collider physics, that third term sounds a lot like the energy. The third part sounds kind of parallel to energy loss in colliders, like PV colliders don't lose as much energy as.
Oh yeah, sure. Yeah, that's synchrotron, right?
Can
Yeah.
think of that kind of similarly?
Sure. Yeah, absolutely. That's quite analogous. If in some cases the same thing. Okay.
Sorry, the diffusion and convection depend on magnetic fields and such, right?
That's right.
You know, galaxies rotating and things are moving around, so they don't depend in time because the timescales are just irrelevant for them.
Yeah, so I'm going to assume that anything that's going on a time scale that I care about, the diffusion constant doesn't change in any measurable way. In fact, in practice, what we really do is we even drop the spatial dependence on this. Okay. It's a spherical cow, but we don't have a better way of doing it. In fact, I'll just, as an offhand comment, there's some reason to think that our spherical cow is broken. If I take a Galprop model, Galprop is a publicly available code that does solves this sort of equation. In Galprop, you generally do things like assuming that these are independent of location, for example. And when you do that, you really don't find any models that provide a great fit to the global data set now, which tells you that diffusion varies from place to place and other sorts of complications. You're breaking your spherical cow model at this point because the data is so good. But that being said, this is perfectly good enough for what we're going to try to do with it. One thing we often do is set this to 0. After all, we have every reason to think the Milky Way is in approximately a steady state. For every cosmic ray that's escapes from the halo or loses energy or spillates or decays or whatever, another one is being injected by a supernova remnant in some sort of steady state way. That's probably a pretty safe approximation, unless you're talking about the spectrum you get in the vicinity of some cosmic ray source that maybe recently exploded or something. Like if you're near a supernova remnant, you're definitely not in steady state, but globally, you're probably pretty close. All right.
Why would you take the gradient of diffusion and convection terms and not the later two?
Well, the gradient is a spatial operation. This is energy losses, which have nothing to do with space. So this is what's going on in space. This is what's going on in energy. All right. right, so to kind of build up a little bit of intuition for how cosmic ray transport works, let's just consider a couple of very simple cases. I mean, I worked with that equation for a long time before I understood conceptually what it was doing. It's a messy differential equation, but in certain limits, it gets very simple. So let's consider a burst of cosmic ray injection. In other words, Q is going to be a delta function in time. And a delta function in location. So there's some object out there, it explodes and dumps a bunch of cosmic rays all at once. And let's say these are protons, so I can neglect energy losses. The solution to this equation is very simple. I'm not going to prove this is the solution, but I'm going to write it down and then explain why it physically makes sense. And if you plug this back in, you will find easily that it is, in fact, the right solution. Okay, so I've introduced this diffusion length scale, LDiff. This is approximately how far, I would say, like the wave of particles has propagated out. Random walking, yeah. Yeah, sorry. For consistency, I'll do that. In R, here is the radial distance from the burst. LDiff, DIF is the subscript for diffusion. It's the diffusion length scale.
And D and that square root of the diffusion is...
That's the D up there.
Okay.
That's the diffusion constant. It's some number, and it's probably a function of, it is a function of energy. So here's the point. If I'm well within one diffusion length, this exponent is close to 1, and I'm just diluting the number of particles by the volume of the diffusion region, okay? So here it's just flat with respect to R, and then around LDiff, this exponentially falls off. And LDiff grows with time. So early on, you have something like this, and then like this, and then like this, etc. So this is a sort of profile evolution you expect to take place as time passes and the particles diffuse farther out. It's a standard random walk in 3 dimensions. So I think it's interesting to think of D as the size of the steps being taken in the random walk. It's not exactly what it means, but you can think of it in that context. And keeping in mind that the length scale traveled goes like the square root of D times the square root of T is good for building up intuition. That will be useful anytime you think about these types of problems. All right, so let's talk about, yeah. That should be squared. Yes, minus R squared over 4L diff squared. So when we take that transport equation, there are a bunch of choices we have to make when you try to set out this problem. With the source term, we have to say we have to say where the cosmic ray sources are. Maybe these are supernova remnants. Maybe this is the dark matter squared. Things like this. You have to say what the spectrum of those particles being injected are. We have some information about this. We have lots of X-ray and other observations of supernova remnants that tell us these things, but they tell us them imperfectly, and usually you fit these parameters a bit to the data. Secondly is the diffusion coefficient. And this is defined like this. So beta is just the velocity of the cosmic ray. D0 is just a number. And then this is the rigidity and a reference rigidity and some coefficient. This is how we usually, or some power. We parameterize it in the following way. Beta usually doesn't matter. I'm not that interested in non-relativistic cosmic rays, or I'm going to ignore that for the purposes of this talk. But bear in mind that it's there. Our best global fits to the cosmic ray spectrum, and I'll explain how this works later, find that this alpha is about 1/3. And I don't have D offhand. There it is. Something like that. That's a 28, if you can't read it. And there's not a minus there. That's a typo, sorry. Sorry, there was a question?
What is rho the rigidity of?
Of the cosmic ray.
What does it mean for cosmic data rigidity? Is that like inertia, is resistance to turning?
So when I say rigidity, I mean the same thing that particle physicists mean. So it's a momentum over the speed of light. Or over velocity. Yeah. You can, for our purposes, and the reason I wrote it in terms of energy here, if you're talking about relativistic particles, I can just write it in terms of energy. I probably need to write down the charge too, but for a unit charge particle, this is the right answer. The third thing are the boundary conditions. Now this is where we kind of get sloppy. What we naively do, and like Galprop does, is they say the galaxy's a big cylinder, and it's maybe 20 kiloparsecs in radius that direction, and maybe plus or minus a few kiloparsecs away from the plane. And we say that all the diffusion and all the properties of everything are the same in anywhere in that cylinder. And once you reach the edge of the cylinder, you just travel off to infinity. It's amazing that it works pretty well. Okay, there's no, I would never be able to justify this without data. But it turns out that's a pretty good, it maps onto a pretty good description of real cosmic ray phenomenology. And what I mean by that is no one thinks that the diffusion constant is a constant until you hit a boundary in which it goes to infinity. That's of course not what happens. What happens is it gradually gets bigger as you move away from the plane. But this is a good approximation of that phenomena, as long as you fit it to the data. So I have at least two new free parameters here having to do with the size and shape of this cylinder. And then instead of writing them down because I'm out of time, I'm just going to mention a couple of other things that go into this equation. So for example, I have a convection velocity, which I might have to specify. I haven't shown it here, but there's this stuff called reacceleration. It involves a parameter called the Alphen speed. That's another free parameter that's often done in these fits. And also, none of this, nowhere in this equation are any of the effects of the heliosphere or the solar magnetic field or solar magnetic wind. You have to do all that stuff too, and that's especially complicated and ugly. Fortunately, most of these things only really matter at lower energies. Once you get above several GeV, the effects of the solar system don't really matter. The effects of convection don't really matter. The effects of reacceleration don't really matter, and the problem gets considerably cleaner. In the case of electrons, even the boundary conditions stop mattering because the particles don't travel that far. So you're really studying the local part of the ISM. All right, so I'm a few minutes late. So we'll stop there and we'll pick up tomorrow and talk about what we have learned about dark matter from cosmic ray searches, and especially those with the AMS experiment on the International Space Station.